In this video, we're going to look at writing the equations of our six trig functions by looking at their graphs. And the first thing that you want to do when you're trying to write the equation from a graph is try to determine what kind of trig function am I looking at. And based on the characteristics of our trig functions that we have six of, our trig functions will either look like a sine or a cosine wave, a secant or cosecant wave, or a tangent or cotangent wave. So we have to kind of narrow down between those three sets of pairs. And then once we identify what kind of pairs of functions it could be, we start finding our key features and then start constructing an equation based on a reference point. And we're going to look here at our first graph here on the top left-hand side. Now, if I'm looking at a wave that oscillates between two fixed y values, up and down like this, and it has no breaks in it, this is going to be the graph of some kind of sine or cosine wave. And so we'll start by writing the general form of a sine or a cosine wave, which I have over here on the right-hand side of the screen. Now, we want to start finding our constants. And to start with, trying to find our constants is I would look to identify the midline. Now, the midline is the middle y value. So I look at my y's and I try to figure out what the middle y is. I start at 4, I go down to -2. So the middle y value here is going to be the y value of 1. So there is my middle y. So that's going to be our midline, which the midline of sine and cosine is k. So our constant k in our equation is going to be +1. Now, the a stands for the amplitude. So I look in reference to my midline, what is the maximum displacement from that midline to get to a peak? It doesn't matter if I go to a maximum or go down to a minimum. Either one of those is going to be a. And looking at our grid, the change in the vertical displacement there is 3. So I have a and I have k. The next thing we want to do is we want to find our period. And if I have a full wave, we have a number of ways to find period, but for sine or cosine, if you have two identical peaks like maximums, the distance from max to max is one full period. And so we look start to finish there along the horizontal, it elapses 8 units. So our period is 8. Now, notice how period doesn't necessarily have a constant here. We've identified a and k. Period, remember, for sine and cosine is equal to 2 pi over w. So I'm going to set the 8 equal to 2 pi over w. And that's going to give me that constant there. And so if I cross multiply and divide from there, w would equal pi over 4. So I have a, I have k, and I have w. Now, to write our equation from the graph, from there, we have every constant accounted for except for h. H are our reference x value. So I have to give you a point to base your equation off of to construct it. Now, what we're going to do here, we're going to look one at a time. We actually can write 4 different equations off of this graph. You actually could write more, but we're going to look at basing on some of our critical points. So if I look here at x is equal to 2, I go to my graph and try to figure out, all right, what is so special about my graph at x is equal to 2? What kind of critical point is that? Well, that is a maximum. Now, the trig functions that we pick, based on starting on a maximum or a minimum, is going to be cosine. So max means we're going to use cosine, and it also means it's going to be positive out front, because if it was a minimum, we'd have to make it negative. So we're going to start plugging everything in. So our equation based on that reference point would be y equals positive a, so positive 3, cosine of w, pi over 4, times x minus h, well, h in this case is 2. And then on the very end, we have plus k, which is +1. So we wrote an equation based on the reference x value of x equals 2. Now, let's look at, well, what about x is equal to 6? X equals 6 on my graph is a minimum. Now, even though it's a minimum, it's still a peak, so we're going to model this function off that point using cosine, but a minimum means we have to reflect it over its midline, so we make it negative out front. So we plug in all of our same constants, a, k, and w. We get y is equal to, we got to make it negative, so -3 cosine of pi over 4 times x minus 6, and then +1 on the end still. And then we look and say, all right, well, what if we base our equation off x is equal to 8? Well, x is equal to 8, we look at that, that is a midline. And if it's a midline, and then to the right of that midline, it is increasing, it's going midline up, we're going to use sine, and sine is going to be positive out front. And so we write our equation here, we'd have y equals a, so 3 times sine of w pi over 4 times x minus 8, and then plus 1 on the end. And lastly here, we're going to look at, let me choose a color I haven't done yet, we'll go with this one, at x is equal to 4. Well, x is equal to 4, I'd actually go backwards a little bit here. I have that point right there, which is a midline. And as we work our way to the right, it's midline going down. Sine is the function we use when we base our function off midline points, and if it's decreasing to the right of that midline, we have to make sine negative. So it would be using sine and negate that amplitude value. And so our equation would be y equals negative 3 times sine of pi over 4 times x minus 4 plus 1 on the end. Now we look here at our second graph. So the second graph we want to write the equation of, I look here and I see a bunch of n's and u's. So I see unbounded behavior, I see a gap in what's going on. This is the stereotypical secant or cosecant graph here. So we identify the types of functions we could use, and then we want to go through and we want to start trying to find our constants here. Now remember, if we have a secant or cosecant graph, it's going to be beneficial to us to identify where the vertical asymptotes are. So I'm going to indicate those here, and that's going to be where I start seeing that vertical unbounded behavior, and I get those noted. And we also are going to want to pay attention to the relative extrema, the relative maxes or mins. Now, we want to identify what A, K, and W are here. It might be helpful for you to remember that really what's going on inside of here is we have one of our reciprocal functions being graphed, and if we wanted to do that, we could graph the reciprocal function where we would just do our best to make our wave through here. And so that way we could see what it is we're working with. Now this is not required, but for some people it makes it a little easier to see what we have. Now remember, secant doesn't technically, and cosecant, they don't have amplitudes. A represents the vertical stretch or the shrink. However, if I want to think of this as the amplitude of that dashed little sine or cosine wave I made, I could do that to kind of help me out, where I'm going to look and try to figure out, well, what is the y value in the middle of those two peaks there? And the y value that's in the middle of those two peaks is going to be negative 1. So negative 1 is that y value that's in the middle. Well, that's going to be what k is. So we have a k value of 1. And then we want to go through here and try to figure out what the A would be, the vertical stretch or the shrink factor. Well, that'd be the displacement from that so-called midline to one of the peaks, and that displacement there is 2 units. And now we want to find the period. There's a couple of ways to find the period, but if I'm looking at this in terms of a sine or a cosine wave, or in fact, even with secant and cosecant, we can find the period by finding 2 identical peaks and figuring out what is the spacing that elapsed in between there. That would give me my period. Well, start to finish, we end up with 8 pi over 16 or pi over 2. Now, just like sine or cosine, the period of secant or cosecant should have been 2 pi, but I applied some kind of stretch or shrink factor to it. That's what our W is. So we'll set the period equal to 2 pi over W. We solve for W and we get 4. So we have all of our constants, A, W, and K for this secant or cosecant wave. We just need to look at our reference X values, which are what the constant H is representing. And so let's go here. We'll look at the very first one at pi over 16. So at pi over 16, I go find what kind of point I have at pi over 16, and it's a relative minimum. Now, in terms of the wave that I drew in between here, Notice how that would have been a maximum. That would have been a maximum of cosine. Now, if that would have been a maximum of cosine, secant is going to be positive just like cosine would be. And so what we would have to write our equation, we would have y equals 2, it's going to be positive because that would have been the max of cosine, times secant of w, which is 4, times x minus pi over 16, and then we have plus 1 on the end. So the next one we would have, we're looking at, is at negative 3 pi over 16, and I look at what's going on at negative 3 pi over 16, and that would have been a minimum of cosine, which means that if I was writing a cosine equation, I have to make cosine negative, and so if I had to make cosine negative, I'd have to make secant negative, so our equation would be y equals negative 2 times secant of 4 times x minus negative 3 pi over 16, or x plus 3 pi over 16, and then plus 1 on the end. So remember that if we would have been a minimum of cosine, then cosine would have had to be negative, which means secant would have to be negative. And in our first one, we had a maximum of cosine, which means cosine would have been positive, which means that secant would have been positive. So that's how I tell, based on the kind of points I have. Now let's go look. We got 2 more to look at for this graph. We want to look at negative pi over 16. And so at negative pi over 16, we go on the graph and figure out, well, what do we have there? Negative pi over 16 is a vertical asymptote. Now, in terms of that dashed little wave I made, it would have been a midline and going up. Now remember from our previous problem, that would have been a midline going up, which means if I was using the reciprocal function sine, I'd have positive sine. Well, if I would be using positive sine, the reciprocal of positive sine would be positive cosecant. So the function I would use based on that vertical asymptote there would be cosecant, and it would be positive out front. And so we'd write our equation as y equals positive 2 times cosecant of 4 times x minus negative pi over 16, so plus pi over 16, and then plus 1 on the end. We're just plugging it into our general form. Now, the last one that we have is looking at 3 pi over 16. And so at 3 pi over 16, I look, and that's another vertical asymptote. Now, in terms of that wave I drew, the dashed wave, the sine or cosine wave, that would have been a midline and going down. Now, like the previous example, if we had a midline and then to the right you decrease, we would have modeled this using sine and making it negative out front. Well, the reciprocal of negative sine is negative cosecant. So my function of choice would be cosecant. I make it negative out front. So our equation would be y equals negative 2 cosecant of 4 times x minus 3 pi over 16, and then plus 1 on the end. So there are models for that one graph. Our last graph here, we look at the behavior of what's going on here. And when you start seeing repetitive behavior of what would look like maybe x cubed, but this is not the graph of x cubed, that's indicative of us having a tangent or a cotangent wave. And when we have that, to help us figure out what our constants are so that way we could write our equation, it's going to be beneficial to us to identify where vertical asymptotes occur at. And so I'm going to identify the vertical asymptotes, and we have a negative 3 pi over 2, positive pi over 2, and then the next one is way over here to the right at 5 pi over 2. And we also want to identify the y values of the point of inflection. Now, the point of inflection is at the true change in the curvature of the function, but I could also cheat this a little bit and remember that for tangent and cotangent, the point of inflection is halfway in between my vertical asymptotes. So I'm going to have one point of inflection here at negative pi over 2, and then the other point of inflection is going to occur halfway in between the other two vertical asymptotes, so at 3 pi over 2. And so now we're ready to start finding our constants. The y value of that point of inflection is what we represent with k. So k is going to equal 2. Our vertical stretch factor. All right, so our vertical stretch factor, if I look at the y value of my points of inflection, and the vertical stretch is what is the change in your y value halfway in between the point of inflection and the vertical asymptote. So when I go halfway there, what's the change in my y value? So I look, and really all I changed here in terms of my y value is I changed 1/2 of a unit. So my vertical stretch, in this case, is technically a vertical shrink, is going to be 1/2, so A is 1/2. To find the period from the graph, you got options here. The period of one of these waves is the distance between 2 points of inflection or even the distance between 2 vertical asymptotes. Either way, that's going to give you the same value. So the period here is going to wind up being 4 pi over 2 or 2 pi. Now, here's the part that we can't forget. For tangent and cotangent, that period should have been pi radians. So I had pi over w, and which means that to make 2 pi, w would have had to equal 1/2. Now we're ready to start figuring out how to write our equation based on our phase shift, or these reference x values. And so we'll look here at this first one at the x value of -3 pi over 2. Well, the x value here at -3 pi over 2 is a vertical asymptote. And so to figure out what function I use based on a vertical asymptote, it hinges on our unit circle knowledge. So we ask ourselves, what is tangent of 0 and what is cotangent of 0? Tangent of 0 equals 0, which means tangent starts at a point of inflection. Cotangent of 0 is undefined, which means we base it off of vertical asymptotes. So since 3 pi over 2 is a vertical asymptote, we're going to model using the cotangent function. So we'd have y equals. Now to figure out if cotangent is positive or negative is real simple. Cotangent should be a decreasing function on the domain. So as I go from left to right, if I'm going down, cotangent is positive. So our equation here would be y equals 1/2 times cotangent of w, which is 1/2, times x minus our reference x value, so x minus -3 pi over 2, so x plus 3 pi over 2, and then we would close up our parentheses and then put our k value on the end, so we say plus 2 on the end. And I almost ran out of room there. All right, now we go look at our next reference x value. Our next reference x value is at 3 pi over 2. 3 pi over 2 is a point of inflection. Point of inflections, we use tangent. Now, tangent was supposed to be an increasing function, but since this is a decreasing function, we're going to have to make tangent negative. So our equation will be y equals -1/2. Zoom in a little bit so I can easier to write. -1/2 times tangent of w times x minus our reference x value, so x minus 3 pi over 2. And then plus our reference x value, or not our reference x, plus k on the end, so plus 2. So there are two equations using two different functions based on that one graph. One with tangent, one with cotangent.